High above our planet's surface, far beyond the blue sky and the breathable air we depend on, lies a region of space filled with invisible danger. Out there, just beyond the edge of our atmosphere, Earth is constantly bombarded by charged particles hurled through space at incredible speeds. These particles originate from our own sun and from the farthest reaches of the galaxy. Left unchecked, they would wreak havoc on our planet, stripping away the atmosphere, damaging life on the surface, and destroying our technology. But Earth isn't defenseless. Surrounding our planet is a powerful and dynamic magnetic field, and within that field are two vast, invisible zones of trapped radiation. These are the Van Allen belts, a natural shield, holding back the worst of space weather and allowing life to flourish below. Though we can't see them with our eyes, these belts are constantly at work. They stretch across tens of thousands of kilometers in space, forming protective rings that silently guard our planet from radiation. But what exactly are the Van Allen belts? Where do they come from? And why are they so important, not just for Earth, but for space travel, communication, and our understanding of the universe? The Van Allen belts are two regions of energetic, charged particles, primarily electrons and protons, that are trapped by Earth's magnetic field. These belts are not solid structures. Instead, they're like massive, invisible clouds of radiation, shaped by the geometry of Earth's magnetic field and constantly shifting in response to solar activity. The inner belt, located between about 600 and 6,000 kilometers above the Earth, contains mostly high-energy protons. These particles are thought to originate from cosmic rays interacting with the upper atmosphere, a process that launches them into the magnetic field where they become trapped. The outer belt stretches much farther, from around 13,000 to nearly 60,000 kilometers above the Earth's surface. This region is filled mainly with high-energy electrons, many of which arrive during solar storms. These electrons move at incredibly high speeds, sometimes approaching the speed of light. Between these belts lies a quieter region called the slot region, where radiation levels are relatively low. But even this zone isn't always calm. The boundaries and intensity of the belts are constantly changing, influenced by the solar wind, geomagnetic storms, and the natural fluctuations of Earth's magnetic field. To understand the Van Allen belts, we need to look at the source of the problem, the Sun. Every second, our star emits a stream of charged particles known as the solar wind. This wind flows outward in all directions, filling the solar system with a constantly moving plasma of electrons and protons. When this solar wind reaches Earth, it interacts with our planet's magnetosphere, the region dominated by Earth's magnetic field. Most of the charged particles are deflected away, following the curved paths of the magnetic field lines. But some particles penetrate deeper, becoming trapped within the magnetosphere. As they spiral along the magnetic lines, they bounce between the northern and southern hemispheres, building up in dense regions, the Van Allen belts. These trapped particles are not stationary. They spiral around magnetic field lines, oscillate between the poles, and drift around the planet. The result is a complex, ever-changing system that reflects the interplay between Earth and the Sun. During solar storms, huge clouds of high-energy particles can be launched toward Earth, supercharging the belts and making them even more dangerous. These events can dramatically increase the number of particles in the belts and shift their boundaries, sometimes even merging the inner and outer belts temporarily. The Van Allen belts serve a critical function. They protect our planet from high-energy radiation. Without them, Earth's atmosphere and surface would be exposed to the full force of solar and cosmic radiation. Over long periods, This could strip away the atmosphere, interfere with the climate, and endanger life on the surface. They are part of a broader protective system that includes the magnetosphere and the atmosphere itself. The belts block and absorb the most harmful particles, allowing only a small fraction to penetrate deeper. This layered defense is one of the key reasons Earth is habitable. Unlike other planets such as Mars, which lacks a global magnetic field and has lost much of its atmosphere. The belts also help protect modern technology. Without them, satellites would suffer constant radiation damage. Communication systems could be disrupted. Power grids could be overloaded. The Van Allen belts absorb much of this energy before it ever reaches us, a silent but vital buffer. But the Van Allen belts aren't just protective, they're also a hazard. For spacecraft, satellites, and astronauts traveling through them, the belts pose a serious threat. Radiation in the belts can fry electronics, scramble data, and harm living tissue. To avoid damage, most satellites are placed either well below the belts, in low Earth orbit, or far above them, in geostationary orbit. Those that do pass through must be carefully shielded and engineered to withstand the environment. During the Apollo missions, NASA had to plan carefully to get astronauts through the belts quickly. By choosing a narrow path and limiting time spent in the radiation zones, the risks were reduced. Still, the radiation exposure during these missions was significant, a reminder that space travel is never without danger. As we prepare to send humans back to the moon, and eventually to Mars, the Van Allen belts remain a critical obstacle. Any crewed spacecraft leaving Earth must pass through them, and the radiation exposure must be carefully managed. Despite decades of study, the Van Allen belts still hold secrets. Between 2012 and 2019, NASA's Van Allen probes, two identical spacecraft, orbited within the belts, gathering data and revealing surprising new insights. One of the most unexpected discoveries was the temporary appearance of a third radiation belt, formed after a powerful solar storm. This third belt persisted for several weeks before vanishing, a phenomenon scientists had never observed before. The probes also revealed that the belts are far more dynamic than once believed. They can change shape and intensity within hours. Waves of electromagnetic energy within the belts can accelerate particles to near-light speeds or scatter them out into space. The belts are, in a sense, alive, constantly responding to the forces of the Sun and Earth. We've also learned that Earth's own weather and lightning activity can send pulses of energy into space, influencing the belts from below. This connection between Earth's surface and its space environment is still not fully understood. Even today, the Van Allen belts remain an active field of research, not only for what they tell us about Earth, but for what they reveal about other planets and the nature of space itself. The Van Allen belts are invisible to the naked eye. We can't see them from the ground. Most people don't even know they exist. But every moment of every day, they are protecting our planet from a hostile universe, absorbing radiation, shaping space weather, and preserving the fragile balance that makes Earth livable. They are part of a vast, interconnected system that begins deep inside Earth's molten core and extends all the way out into interplanetary space. They remind us that our planet is not isolated. It is part of a living, dynamic cosmic environment. And as we venture farther into space, toward the Moon, Mars, and beyond, we must continue to study and understand these belts. Because while they protect us here on Earth, they will also test our ability to survive and thrive beyond it. The Van Allen belts, Earth's magnetic shield, are a perfect example of how science, nature, and the mysteries of the cosmos come together in the space just above our heads.